Dear students, let us discuss now about the Norton's theorem. Like Thevenin's theorem, Norton's theorem is also used to simplify the complex electrical networks into simple electrical networks. However, unlike Thevenin's theorem, we do not have any series combination of the circuit elements here in the equivalent circuit. Rather, we have the parallel combination of the circuit elements. So this theorem states that any linear bilateral network containing one or more energy sources and passive elements, right? So uh, in superposition theorem, we had minimum two energy sources must be there in the network, but in this case we must have at least one energy source or more energy sources along with the passive elements. So any such network which has all these circuit elements can be replaced by a simple network which contains a single current source. Now this current source is known as IN, that is Norton's current. And then we must have a single resistance which is known as Norton's resistance, and it is represented by Rn. So that means any such network which has like all these sources and passive elements, so any such network can be converted into a simple network which just contain a current source and a resistance connected in parallel to one another across the load terminals. So that means we do not alter the load terminals. Apart from load terminals, whatever we have in the network, other than load terminals, other than load resistance, whatever we have in the network can be replaced into a simple network. That means if there is a complex electric network, so this is, let us say, complex electric network, and we have the load resistance RL connected across the load terminals AB and has some current flowing through it. So this part of the electric network can be converted into a simple network which contains a current source known as IN and a resistance known as Rn, means the Norton's resistance, across the same load terminals, means this resistance will be connected here now. So we can find out IL here. Okay, so that means we have converted this into a simple network. So this part is known as Norton's equivalent, only this part, right? So from the statement of the Norton's theorem, we have understood one thing, that if we have to obtain the Norton's equivalent of the given network, we need Norton's resistance, we need Norton's current. Now the question is that how to calculate Norton's resistance and Norton's current. First of all, we must understand what is the Norton's resistance. Basically, the Norton's resistance is the equivalent resistance which is calculated from the open load terminals of the given complex network by replacing all the sources with their internal resistances. That means voltage source, ideal voltage source is replaced with a short path, and ideal current source is replaced with open path, because voltage source has zero resistance and current source has infinite resistance. So from this statement of Norton's resistance, it is observed that Rn is similar to Rth. The only difference is that it is the Norton's and it is for Thevenin. But these are same, right? Now, how to calculate RTH? So step 1 is calculate RTH, not RTH, sorry, I apologize. It is Rn. So first step is open the load terminals, and second is replace all the sources with their resistances, right? And then third is redraw the circuit. Do not forget to redraw the circuit. The second step in solving a network using Norton's theorem is to calculate the Norton's current. Now, to calculate the Norton's current, we have to apply these steps basically, or we can say that we need to know all these points. Now, the first thing that we do is that we remove the load resistance from the given complex electric network. After removing the load resistance, we short the load terminals. Then, under these circumstances, whatever current is flowing through these short load terminals is known as Norton's current, because This current is determined by short circuiting the load terminal. So we call this current as short circuit current, and it is represented by ISC. Then step 3 is draw the Norton's equivalent of the given network. Now the Norton's equivalent consists of a current source, which we call as ISC or IN. Then we have a resistance, which we call as Rn, and then we have the load terminals basically. So this is, let us say, RL, so AB, right? So we can find out the value of RL. So this was the third step. So whatever value of Rn and ISC is obtained in step 1 and step 2, we will use that value here, and then we can find out the value of load current by using the equation as given here. So in step 4, uh, calculate the load current if required. Okay, so how will we find out the load current here? That we can understand. Now in this circuit, let us say this is some junction X. So when this current will come, this ISC will come to this junction X, it will divide into two parts. Let us say this is I dash and this is IL. So by using the current division rule, IL is equal to, now what is IL? IL is flowing in this branch here. So it is the part of this ISC or IN, let us say. So it is ISC into resistance of the branch opposite to this load current branch, right? And the opposite branch is this RN. So we will write Rn here, and then we'll divide by the sum of these two resistances. So this is the equation for load current as far as the Norton's theorem is concerned. So let us apply these steps on a dummy example. Let us consider a circuit as shown. And the circuit is, we'll take the same circuit as we took in the Thevenin's case. So this is plus minus V is here, and now we have this R1 here, then we have let us say this R2 here, and then we have R3 in this case, and then we have a load resistance here. This is RL, and these AB are the load terminals basically. This is, let us say, junction X here. Now this part of this network will be converted into Norton's equivalent. So it shall be converted into Norton's equivalent. Now let us understand this thing. So let us apply all these four steps one by one. So step 1 is calculate Rn. Now how will we calculate Rn? we will we will remove this load branch and replace this with its resistance, right? Ideally the resistance of voltage source is 0, right? So we will redraw the circuit and we'll see how it looks like. So let us redraw. So we have removed the voltage source and we have short circuited it like this, and then we have a resistance here which is R1, and then we have a resistance here which is R2, and then we have a resistance here which is R3. Now we have made the load terminals open, and we will calculate the Rn here by looking into the network from the open load terminals. So we'll see that these two are in parallel. So Rn is equal to R1 is in parallel with R2, and the combination of these two is in series with R3. So it is R3. So Rn is equal to R1 R2 divided by R1 plus R2 plus R3. So this is how we can calculate the value of Rn, and it is similar to the case of Thevenin's resistance. Now let us come to step 2. So step 2 is calculate In or ISC. Now to calculate IN or ISC, what we do, we simply replace the load resistance with a short path, right? Rest of the things are not altered, they are not changed. So replace the load with a short circuit and redraw the circuit. Now let us redraw the circuit here. So we have the voltage source V plus minus, we have resistance R1, we have resistance R2 here, then we have a resistance R3, and then we have these load terminals AB. Now what we have done is we have short circuited these load terminals. So whatever current then flows in this particular path is known as ISC or IN, right? So how will we calculate this ISC or IN? That again depends upon the circuit analysis that you know. You can use any method, mesh, node, uh, current division, voltage division, whatever, right? So let us say some current I is delivered by this particular source, and this I will flow through this R1. It will come to junction X. So at junction X, this current will be divided in this branch and some current will divide in this particular branch. Let us say this current is I dash. So how will I find out ISC or IN? So IN in this case can be calculated as, because at junction X this ISC is being distributed and it is the part of I. So the I current into the resistance opposite to the branch in which ISC is flowing. What is that branch? It is R2. So I'll write R2 here and then sum of these two resistances which are in parallel. So it is R2 plus R3. So this is how we can find out the value of Rn in this case. So that means to calculate the value of In, we need I. So I can be calculated as V by R equivalent. Now this R equivalent is different from the Rn. So R equivalent in this case is R2 parallel R3, and then we have this in series with R1, right? So we can put the value here. We know the value of V also, so we can calculate I, and then we can substitute the value in this equation. Now step 3. So step 3 is draw the Norton's equivalent. So Norton's equivalent for any circuit, whether it is complex or simple, the Norton's equivalent is same for every circuit. So it is shown by this uh, current source, which is ISC, and then we have a resistance here, which is Rn, and then we have the load terminals here, AB, and the load resistance is connected here. This is RL, and let us say IL is flowing here. So in step 4, we will calculate the load current, which is already discussed. It is equal to ISC into Rn divided by Rn plus RL. So this is how we apply the Norton's theorem on an electric network to simplify it to find out the load current in the load branch. So this is it for this part of the lecture. Thank you so much.